We are all very aware of the contradictions we live in. We want this ideal world and ideal environment to live in. At the same time, we want to be able to export goods, we want to be able to import goods, and we want to be able to trade. And in order to ship goods around the world, we need shipping. And at the moment, we're faced with climate changes and things like that, and we know what contributes to it. And in this particular scenario, shipping of those goods that we want to send around the world contributes a massive amount of pollution. Once upon a time, we got around the world, we sailed around the world, we discovered new countries, and we harnessed the power of the wind, and we had these beautiful big square riggers, and they were our container ships. This is going back 100, 200 years ago. And we lost touch with being able to harness the wind, and instead we went to diesel, and we put our goods in containers, and we put our containers and we stacked them high up on top of giant container ships, burning huge amounts of oil, and we shipped stuff around the world. So container wings is a solution for contributing forward motion of a ship, harnessing the power of the wind. These wings are fully adjustable. They're telescopic. They raise, they lower, they rotate according to the wind. And putting them on top of the last row of containers of a ship allows us to put back this big giant sea of sails, this sea of wings that can help reduce fuel consumption. And by reducing fuel consumption when the wind is right, it means we reduce digging up all this fossil fuel, and we reduce emissions that contribute to climate change. The container wings that you see here are part of a really sophisticated system. There can be literally hundreds of these things on a ship, and they're all rotating autonomously, finding the best angle to pointing towards the wind and contribute towards forward motion of the ship. They all talk to each other, they all know where they sit relative to each other, and through a wireless network, they're all controlled back at the helm of the ship. So not are they only autonomously controlled, but they're obviously controlled manually as well in varying weather conditions. And as the wind changes, they can be lowered. So container wings can be adapted to any ship. So looking at a bulk carrier, the containers can be mounted to the lids that open up above the containers, and you can contribute to reducing the amount of fuel that's used, and contribute to lowering your emissions by including a mechanism that uses wind to assist in forward propulsion. On this ship we can see 20 containers, each carrying 4 wings, and they're 50 feet in height per wing. The nature of shipping and logistics means that the wing containers can be located at various ports. They can be picked up depending on the run. So if there's going to be a crosswind run or a downwind run, maybe a ship really wants to stock up and load up heavily with the wing container system. Maybe there's not that many available in a port, but they can pick up whatever's available at the time. And particularly if they're expecting crosswinds or downwind runs, the surface area and the actual wing shape of the container wing is obviously going to contribute towards forward motion as best as possible. The shipping of containers is an amazing logistics game, and as part of shipping, ships need to know what the weather's doing at all times. Yes, they run to deadlines, but if you're in a position where this ship is running downwind or a crosswind, and it can pick up enough of these container wings to contribute towards lowering fuel consumption and lowering emissions. The software allows for delivery of the containers to be loaded on last as part of the ship's organisation. They get unloaded first, they get put aside. The swapping of containers gets done in a port, and then of course the container wings get put on last. And of course, being containers themselves, they don't need to have their wings up. They can be shipped around the world just as regular containers. So when we're looking at the containers, one of the obvious things you can see here is the red wing and a green wing. The red wing are for port side winds and the green wing is for starboard side wings. And typically you'd only have one or the other. They very deliberately haven't been built as a symmetrical aerofoil shape. They have been given a particular aerofoil shape to try and maximize lift with low drag. And there's 4 modules. There's 2 starboard wings and 2 port wings that fit into a container. With the horizontal discs removed, you can see how the telescopic action allows the wing to fold down and collapse upon itself. They sit inside circular holes, obviously, because they need to be able to rotate fully. And when they're closed, when they're down, the roof is actually sealed. We're just having a bit of an opportunity to look inside the container of the shape of that aerofoil wing. They're deliberately not symmetrical. They're deliberately in an asymmetrical wing shape. We do this because it's far more efficient. Looking at the containers themselves, they've obviously been modified. So this is a 40-foot shipping container. It's had 4 holes cut into the top of it. And the wings, there's 2 starboard wing modules and 2 port wing modules. And they are simply forklift in, and each of the modules can be easily taken out and loaded back in. And we'll see in a moment that they are completely self-contained, so all of the smarts about them are built into each of the modules. Each of the modules contain batteries for all of the operations, so the lifting and the rotating of the wing structure. Here you can see banks of batteries and next to them generators. A little later on I'm going to show you in detail just how the units go together. So this shipping container is a standard shipping container. They can be built as a double shipping container, but it makes it very difficult to obviously transport them around when not on ships, i.e. via the road. So let's have a look at the individual units themselves. At the base of the wing, you'll be able to see 2 winches. These what are known as captive winches. They're electrically operated, and they're connected to cables, and the cables are rotated around a drum, and when wound up, they lift the telescopic action of the wing. This one has 5 units on either side. This one you can see the telescopic action is partly up. The winches, there are 5 captive winches at the base for the 5 individual sections, and also we need winches to be able to pull these things down. So when they're under strain or immense amount of pressure, sideways pressure, they become really difficult to pull down. You can see the battery pack at the front end or the rear end of this unit. Typically at the rear end, it means that the forklifts, it's a huge amount of weight to put in there, so the forklifts can access it from this side, or sitting on 316 stainless steel. You can see the battery charges per bank there. And there's also what's known as screw jacks. These are an electrically operated screw jack that pushes the unit up into that ring. You can see the white ring at the top there. That gets pushed up against the ceiling, making it a really good snug fit against the ceiling, and the feet go down and lock it into the base of the container. The wing itself rotates around. You can see at the base there, there's some drum rollers there. There's a gearbox on each of the corners which drive it, and you see those motors. There's 2 on the bottom and 2 on the top rings, and they drive it. There are 7 rows of 4 batteries, 28 batteries in total. There's a 24 volt system on a 316 stainless steel frame. These batteries are 250 amp hours each, and you can see next to them the chargers, the battery chargers. Now each container has a series of generators, or these can be powered up via the ship's power. In front of us, that black round object is the one of the motors that drives the rotation of the wing. You can see there the handles, which are part of the screw jacks. There's actually an electric motor inside this corner here. The handles are there as a backup for manual operation, and of course that very, very important top ring to make it fit into the top of the container very snugly. So looking at the modules inside the container here, The last component that goes into the container is the generators. The generators are left to one side because we want to be able to have service access down the side there. So you can see this nice clear avenue from the front of the container to the rear of the container, and the service technicians can get into the space and access all of the winches, all of the batteries, all of the chargers, everything that they need to do their service and maintenance on inside the container. So the container contains the 4 wings. The side of this container has obviously been removed so that we can have a look inside of it. And so each of the modules, when they go into the container, they are effectively pushed together, nice and tight, and they get locked into the floor, they get locked into the ceiling, they become absolutely fixed in position. There's enough working space inside to be able to manage the batteries, manage the chargers, and service all the motors. You can see here this red wing, the port side wing, is extended fully. Next to it is an open hole that we can see the wing inside of it and the ring structure. That's really important to seal into the top of the container. On the left, the round disc. This is the top of the very final disc that sits on top of the wing, and when these are retracted, it comes back and actually makes a seal on top of the container. So when they're all retracted, the container is nicely sealed and weatherproof. The wings themselves are designed like a glider wing, so we're looking for maximum lift and least drag, and we can achieve this with a very tall, narrow structure. The leading edge, the curvature of the leading edge is highly important, and the sharpness of the trailing edge is also really important for not creating disturbance for the other wings. Each of the wings have a series of wind instruments, so direction and speed, and they all talk to a central processing unit, and this processing unit allows the wings to be directed and turned to be most efficient at all times. The standard module is designed to fit in really snugly, so it's 2.4 by 2.4 by 2.7, which is the internal size of a standard shipping container. And in the 40-foot shipping container, we can put in 4. Typically, only 2 of those sails will ever get used at a time. So either the 2 starboard or the 2 port side wings will ever be extended up. You can see here a module being ready to be loaded in. It is a standard size forklift can pick up all of the modules. The modules are designed to be able to be built, obviously, serviced anywhere around the world, repaired on the go, swapped out at various ports where servicing is available. The frames are made out of steel. There are stainless steel components, and the wing itself is made out of marine grade aluminium. It needs to be very strong. It needs to be able to be cut and shaped and welded. And it also needs to take considerable loads. You might be wondering what those round discs are between the segments. So they're designed as the wind is swept up the sides of the ships. They trap the air and ensure that it runs perpendicularly over the surface of the wing for maximum efficiency. So whilst we might be in the process of developing new technologies and new power like hydrogen fuel, for example, in the meantime, what we could be doing is contributing to reducing fuel, reducing emissions by adding the container wing to container ships. It's not likely that our reliance and dependence on container ships is going to go away. And until those hydrogen-fueled engines come in, let's contribute to making these container ships more efficient and cleaner on our environment.